Alright, today for our acids bases unit, we're going to be working with the pH scale. We introduced to this a little bit in our previous unit and in the beginning of this unit, but we're going to get a little bit more into the calculations involved. Now, that one thing I want to point out is that at any pH, we have some presence of hydroxide and hydronium ion concentrations. At our higher pHs, the more basic solutions, we have a higher hydroxide concentration compared to our lower pHs, where we have a stronger acidic solution with a higher hydronium ion concentration. One relationship I want to point out is you'll notice that our concentrations, their exponents, are always going to end up equaling negative 14. So kind of keep that in mind as we move ahead with these calculations. All right, we were introduced to this equation at the end of our last unit. We're going to be using this in a couple of our calculations that our pH is equal to the negative log of our hydrogen ion concentration. Now in pure water, we determined that hydrogen ion is always going to be equal to 1 times 10 to the negative 7, which gives us a pH of 7. So I first want to point out this relationship of when we have as our base number here 1, we can actually use our negative exponent to determine our pH. Now, when adding an acid or a base to water, the concentration of our hydronium ion and hydroxide ion is going to change and adjust in order for the ionization constant of water to always remain at 1 times 10 to the negative 14. So for acids, hydrogen will increase while hydroxide decreases. Bases, the opposite is true. And then in neutral solutions, those two concentrations have to be equal. Now, for strong acids, we can use the concentration of the acid to determine all of these variables. Because we have a strong acid, it's going to completely ionize in solution, so the concentration for acid is also the direct concentration of our hydrogen ion or hydronium ion. Now, when our base unit here is 1, we can always take the exponent of hydrogen to determine our pH. And you can try this out by plugging it into the formula, and you'll see that we get a pH of 1. Now, hydrogen ion concentrations and hydroxide ion concentrations are always going to, again, their product equal to 1 times 10 to the negative 14th. So with that in mind, I can determine then that our hydroxide ion concentration is 1 times 10 to the negative 13th. So again, these exponents, when these numbers out in front or base units are 1, these should always add up to negative 14. Now, our pOH scale, we don't use that often. However, it is available and is based on hydroxide ion concentration. So very similar as to how we got the 1 in pH, we also know that our pOH then is equal to 13. And here you can see that pH and pOH here should always add up to 14. All right, now we're going to work with a strong base. Same idea that all of the potassium hydroxide is going to dissociate into water, so we can use the concentration of the solution for the concentration of hydroxide. Similar idea before is we can use the exponent negative 2 to determine that our pOH would be 2. And then the same ideas is that hydrogen ions is going to be equal to 1 times 10 to the negative 12. Again, because these are simple ones out in front, these must add up to negative 14. And then our pH is 12. So these two relationships you need to definitely be aware of, because it allows us to analyze and look at some different variables, because those two are always going to hold true. So for acidic solutions, again, we've talked about how hydrogen has to be greater than hydroxide, meaning that hydrogen has to be greater than 1 times 10 to the negative 7, and hydroxide has to be less. For basic solutions, the opposite is true. And then for neutral solutions, we know that those hydrogen ions and hydroxide ions have to be equal to each other, and thus must be equal to 1 times 10 to the negative 7. The product of those two is always going to equal 1 times 10 to, and that should say negative 14th. Now, one thing is we have to be able to compare various pH values to each other. If we have an acid with a pH of 2, it's actually 10 times more acidic than a pH of 3, meaning it has 10 times as many hydrogen ions as that solution with a pH of 3. An acid with a pH 2 is then 100 times as many hydrogen ions as an acid with a pH of 4, and so on. So just kind of keep that in mind because of our formula that we work with. Every jump on the pH scale of 1 is really an increase of 10 times the either hydrogen or hydroxide concentrations, depending on which direction you move. Now here we're going to do a couple of calculations with some strong acids and bases. At the end, we'll use a weak acid. So here we're going to calculate the pH of that 0.15 molar solution of nitric acid. This is a strong acid, so that solution's molarity I can use as the hydrogen ions concentration. Here we have that our formula that we're going to use, which we were introduced in the beginning of this lesson, is that our pH is equal to the negative log of our hydrogen ions. So we're going to go ahead, plug our concentration in, plug this into our calculator to get 1.82, and that's our pH. Now, determining the concentration of hydroxide, which was the second part of this question, I can also take my molarity and plug it into this formula, knowing that the ionization constant of water is that 1 times 10 to the negative 14th, which gives us the concentration of hydroxide as 6.67 times 10 to the negative 13th. Here we're going to work with a strong base. So again, the concentration of the solution for the strong base is also the concentration of hydroxide. I want to know the pH value, so I'm going to find the concentration of hydrogen in order to do so. And we can either relate this to the fact that because we're working with these simple units in terms of 1 being our base, or we can just simply plug it in and find that hydrogen ions are equal to 1 times 10 to the negative 10. And then finally, because of this value, you can go ahead and either plug this into our pH formula and take the negative log of this concentration, or recognize from a couple of slides ago that when we have 1 times 10 to a negative power, that power is also equal to our pH. And then finally, we're going to work with a weak acid, and we'll practice this more in class tomorrow. But because this is a weak acid, it's not going to completely ionize in solution, so we can't just plug in 0.025 molar. We're going to go ahead and use the ionization constant of an acid, products over reactants. We're going to go ahead and plug in our concentration of HF, and then plug in our ionization constant, which is coming from the back of your reference or your note packet. We're plugging in X for each of those based on the ionization formula. And then we can determine that X, or the concentration of hydrogen ions, is 2.96 times 10 to the negative 3. Now I can take that to determine the pH using the negative log of that hydrogen ion concentration, and then by doing so I can determine that the pH of this weak acid is 2.53. Alright, so that is it. So we talked very briefly, and we'll go into more practice tomorrow about relating pH, pOH, and the hydrogen and hydroxide ion concentrations, going from very basic, as you saw in some of the slides, to more complex, as we did at the end. So go ahead, just review your notes. There's no quiz or summary for this unit, so you are all set.